I'm Yao. I'm a faculty member in Stanford. And today I'll tell you about some of the recent progress we made in my group to enhance the representation accuracy of neural networks. And I'll explain why we want to do that. In particular, we have an interest to use it to acquire highly accurate numerical solutions to PDEs. And towards the end, I'll talk about an example of using this to find singularities in fluid. So yeah, the title of today's talk is Machine Precision Neural Networks for Multiscale Flows. As some of you may know, neural networks are widely regarded as a universal function approximator and is widely used to approximate multiscale functions or even operators. One of the examples that have been talked about a lot these days is the AI-based. This is an example of a machine learning-based model that can make weather forecast. And this is a global wind field. And you can compare that with a classical numerical solver for the weather. So this is, sorry, I won't tell you which one is which. But if you look at these two maps, one of them is from the classical numerical weather prediction model. Another one is a neural network-based weather prediction model. So I usually ask people whether they know which one is AI-based and which one is numerics-based. So how many people think the left one is an AI-based, machine learning-based model? A few. What about the right one? Okay, so 50%. Yeah, I mean, it's basically you cannot really tell, right? It looks pretty similar. But if you look closely, the neural network machine learning-based model usually tend to capture the large-scale feature very well while missing the fine-scale details. So in this case, this is the one that's generated from a numerical simulation that numerically solves the partial differential equations that give you the structure of these fine-scale details that's not really seen in this neural network-based model. And you can see that more clearly in the spectrum. So this is the Fourier spectrum of the global wind field. The black line is from the ground truth, the numerical simulation. The x-axis is the wave number. The y-axis is the density. The colored lines are various different AI-based weather prediction models. So you can see that the AI model agrees, the spectrum from the AI model agrees with the ground truth at smaller wave number, meaning that it's capturing the large-scale features, but you really deviate from the ground truth for larger wave numbers. So it's really missing all the fine-scale details. Quick question. Okay, clarification questions. Yeah.
Why doesn't the AI give you a plane structure but the wrong plane structure?
I think your question can be answered with the future slides, if that's okay. Yeah. So this is actually quite problematic, right? Because the motivation to use a neural network is due to the fact that it's considered as a universal function approximator, but in reality, it often fails to capture the fine-scale details that is present in the data. And this is also called the spectral bias of neural network that was first reported in his 2019 paper. This is a very simple illustration of that. So the blue curve is the target function we're trying to fit. The green curve is the neural network approximation. And you can see that as you train a neural network, it tends to first prioritize fitting the low-frequency signal and then takes much longer iterations to capture the high-frequency, the fine-scale details. So the spectral bias refers to neural networks' tendency to prioritize fitting frequency with certain frequency range. And this is a problem because a lot of the data, a lot of the function we want to fit exhibit multi-scale features. Okay, so this is today's outline. First of all, motivated by this problem, I'll talk about an algorithm we developed that can boost the approximation accuracy of neural network down to machine precision, and it can be used to tackle the spectral bias that I just talked about. And I'll talk about examples of extending this neural network to approximate solutions to PDEs numerically. And finally, I'll talk about the examples of application of these methods for finding singularities in fluids. Let's get started. And some of you have seen this before. To set the stage, I just want to give you a brief introduction of what the neural network is actually doing when it approximates functions. So this is a fully connected neural network. Neural network is basically a model for functions. So here, the neural network maps a scalar input to a scalar output, u of x. And when you pass information from the input x to the first layer, you're doing a very simple calculation by multiplying the input with a constant weight plus a constant bias, where the weight and bias are fitting parameters. And then you apply a nonlinear activation function. Therefore, this is the output of a neuron in the first layer. And common choice of this activation function, it's your choice. You can use hyperbolic tangent or sinusoidal or other options. And you can do that for all of the neurons in the first layer. When you pass information from the first layer to the second layer, you do a very simple operation by multiplying the output with the corresponding weight and sum them together. And then you can write down an analytical expression of the output of the neuron in the for a neuron in the second layer. And you can just do exactly the same thing for all of the neurons throughout different layers and different width throughout the widths. So essentially, you can analytically write down an expression of the neural network output as a function of input. It's quite nasty, but all that matters is that this expression contains lots of free parameters, which are the weights and biases to be determined. And it has been shown in 1989 by Hornick that you can use a fully connected neural network as a universal function approximator. In fact, if you reduce the layers to just one single layer, and then if you choose sine or cosine as your activation function, then the neural network converges to something that's quite similar to a Fourier series, where this is an expression of this neural network, and the weight connecting the input to the neuron represent the frequencies in your Fourier mode, and the weight connecting the neuron to the output represent the amplitude of different Fourier modes. So if you're trying to fit a function that's more periodic, you might consider choosing your sinusoidal or cosine as your activation function. But if your the target function you're trying to fit is very, delta function or Gaussian-like, it's not good to use sine, because then you need infinite number of modes, and that's not an efficient use of neurons. So in that case, you can just change to hyperbolic tangent or other activation function. Okay, so to use this we can use the neural network to fit curves. And all you do is neural network output a function that's a continuous description of its input. And when we are trying to train the neural network, we are essentially we're solving an optimization problem where we are trying to find the optimal choice of the weight and biases such that it can minimize the cost function. And the cost function quantifies the distance between the data points and the continuous neural network prediction. Okay, so here's the fun part. Here, Yangji was working on this with me as a postdoc, and now he's a postdoc in Koran. So if you're interested, I encourage you to talk to him. But here, we're curious what limits the approximation accuracy of neural networks. So here we are just trying to fit a very simple 1D function. So the y-axis is the output, x-axis is the input. The blue line is a made-up analytic function we're trying to fit. The red dashed line is the neural network approximation. And here, the loss function quantifies the distance between the neural network prediction and the ground truth analytic function. So the loss function goes down to about 10 to the minus 5 throughout iterations. And this is already pretty good for most applications. But the question is, why not even lower, right? If your neural network is truly a universal function approximator, why can't the error get smaller?
So can I just clarify? So
Yeah.
you're just training on this curve and then fitting this curve and training it on a million curves and then trying to see how well it does on this one.
Right, so we're just trying to, very simple task, just trying to fit this one curve.
Okay.
And even that, the accuracy is kind of, seems like it cannot get lower. And this is very common. I think for most of the machine learning paper, you see the error don't really go down farther than this, right? So of course, we try to. This is training, but testing is also limited.
But this one specifically is training.
That's right. So I don't know if anyone, if you have training experience, you probably see this kind of thing. Your error is like limited. And the first thing to try is to what if you increase the number of training parameters? So we increase the depth and the width. That's the typical things people do. We are training for a longer time, but none of those can solve this problem that the error just converge over iterations. So that motivates us to develop this multi-stage scheme, which in one sentence is trying to use a second neural network to correct for the error that's not learned by the first neural network. So the block line is this multi-stage scheme, and you can see that you can effectively reduce the error, in this case, down to machine precision. And the total parameter of the multi-stage neural network is less than the total parameter of this single neural network. Therefore, the computational cost is actually smaller compared to a regular neural network, but you can effectively get the error down. So before talking about this algorithm, I want to draw your attention to this, I thought, a very elegant analysis that explains the origin for this spectral bias of neural network. So as I said earlier, if you have a single layer neural network, you can express your neural network as this, where X is your input, and W, B are the weights and bias. They are the parameters of your function. And the J is the loss function that measures the mean square distance between the neural network prediction and the target function that you're trying to fit. So here you can, we denote U hat as the Fourier transform of the neural network prediction U. So you can write everything in the Fourier domain, and then you can show that throughout the optimization procedure, we are trying to minimize the cost function of the neural network based on the gradient of the cost function with respect to the parameters we're trying to optimize. So this gradient governs how fast you can converge the error. And it can be shown that this gradient decay exponentially with k. K is the frequency of the neural network prediction. So this is terrible news because that means this gradient will be very small when your neural network function has high frequency. Therefore, it would take very, very long number of iterations to capture high frequency signal. And this is a very simple illustration of the origin for the spectral bias. And to tackle this problem, the first thing you can do, a very simple fix, is to, if you look at this exponential decay of the gradient of the cost function, the decay rate is characterized by the wave number rescaled by W, which is the weight of the neural network in the first layer. So the first thing you can do is simply rescale the weight, the neural network parameter, proportional to the frequency of the target function you're trying to capture, so that you can make sure this K over W stay large for large frequency. Therefore, you can now activate, you can make this gradient large for large K and activate the learning for high frequency functions. And this actually works pretty well. So you could simply, in our implementation, we just have a scaling factor kappa that's a multiplier of the weight of the neural network. And kappa is you can define this parameter based on the desirable frequency you're trying to fit.
But kappa times W is just like the old W. If the system chooses its own W, so how can it make
good question. So neural network actually, W usually is within orders of magnitude 1 in the optimization algorithm. So W is actually not freely, you cannot go to infinite large values. That's why we have to give a helper kappa. Yes. That's right. That's right.
So in principle, you could just put a norm that will manipulate the exponential.
I think that's a really interesting exercise to see how this behavior change. I definitely have seen papers that shows that if you use a default norm, you can tackle the bias. But the bias, I don't think it goes away. It's not a simple exponential, but I don't think it completely go away. But that's a good numerical exercise to try. So, okay. Okay, wait a few slides. Wait a few slides. Yeah, so that was just how do you deal with high frequency functions, right? But there's an independent issue, which is really the issue we're trying to solve. When the training error is very small, the optimization the learning becomes very slow, right? Because you're learning from very small errors. So this is the main idea of the multi-stage neural network. Here we express the function we're trying to, we express the neural network as a superposition of several different neural network, where U0 is from one single network that capture the leading order signal, and then we have higher order error terms that's captured by a subsequent neural network, U1, where this epsilon 1 is some constant that's very small. This represents the magnitude of the error that's from the first neural network. And then you can also, of course, write down subsequent higher order terms for in this superposition. So the nice thing about this is that neural network learns orders of magnitude 1 functions very well. So here, instead of forcing one single neural network to learn all the details, we have a set of many different neural networks, and each is responsible for learning the function of different orders of magnitude. So this, of course, this idea is not completely new. There has been several other papers with similar flavors, but we, in the next slides, we will combine this with the idea of learning high-frequency functions. Okay, so here is a numerical demonstration. Again, this is another simple 1D function. We're trying to fit. The y is the output, x is the input. The blue line is the made-up analytical function. The red dashed line is the neural network fitting. And here, after one single neural network, you can measure the distance between neural network prediction with the ground truth with the target function. And that gives you something like this, where the error is on the order of 10 to the minus 4. And this is when it's already pretty hard to get the error farther down with a single network. So now using a second neural network combined with the first one, the second neural network now has an error that's down to 10 to the minus 8. And one thing that's worth noting is that this error of the second neural network has a higher frequency. So if you look at this, you do a Fourier transform on this, you can look at the dominant frequency of this second neural network. And then if we do a third neural network to fit the error from the second neural network, you get the error of the third neural network becomes 10 to the minus 11, now have even higher frequency. And then you can just keep doing this until the error reach the desired precision.
Can you elaborate a little bit on what's the data that you use to do this? Is this online learning? Are you doing mini batching in finite data sets? What?
It's really.
Mic, please.
Oh, we're using. I think that the question is a good question, but that doesn't really matter. We are not using any fancy batching methods. It's just using. The sampling. Are you guys asking about the sample? How many points we are training on? Or?
How many points and whether you.
Next to you is the.
While Eric is trying to figure out, I just want to say.
Thank you. I'm asking not only how many points you use at every stage, but whether you refresh the batch. Is this online learning? Because otherwise, I don't see how you can get, this amount of precision if the data set is finite. So I suppose it's online.
Good question. We are testing this using analytical function because then we can sample infinite. We can sample as many data as we want. So here we get to control how many data we sample. So we try to make sure we have about 10 data points per period. Does that answer your question? And then we use all of the points for training.
But then you refresh the X. There's the input and output data. You refresh the X. You do online in X, like you will do in PIN, for example, later on, or no?
Can you define online? What do you mean by online learning here?
That the data set is not fixed. That at every iteration you redraw.
With a higher stage, if you want higher error, you definitely need more density of data points. Yeah.
But you need to fit the X. You cannot evaluate these integrals.
There's also a Q&A session towards the end, so I'll try to make sure. This is the first part of the talk. So, but it just show that actually Eric mentioned a very good point. Very often the function you are trying to fit is not analytical, right? Because if your data point is finite, that will actually limit the error you can get, right? So here we're just trying to show that if our data, you can go down, we can address this expressiveness problem if we have the privilege to have as many data points as possible. Okay, so and usually in ML talks, you want to see how the error converges with iterations. So just to show that the convergence rate is very, very good compared to just having one single neural network. One thing that I thought was quite interesting and we don't fully understand is that we observed some interesting scaling laws of this type of multi-staging neural network. So as you see here, when you add the expressiveness of the neural network by adding subsequent neural networks, by adding the second and third stages, the error not only have smaller amplitude, you also have higher frequency, right? So if we plot throughout different stages, stage 0, 1, 2, 3, the error versus the characteristic frequency of the error, we see a very nice scaling behavior that's relatively robust against a few functions, a few arbitrary target functions that we have tried. And it's also robust against varying neural network depth and number of layers. So pretty much, it's like something we saw. The frequency of the error scales with the error to -1 over alpha, where alpha is 6. So who cares about this? It turns out this can be desirable because, let's say the error of fitting a target function is epsilon. If you have a very large alpha, that actually give you the ability to approximate derivatives of the function with high accuracy while you take higher order derivatives. So what I meant is that if you estimate an error of the derivative of the function you're trying to fit, and you have this power law, you can write down that the nth order derivative of the function scale with epsilon to the 1 minus n over alpha. So if you have a large alpha, you can take more number of derivatives while keeping the error of the derivatives small. Exactly. good point. And neural network is universal function approximator, but there are also many other universal function approximators, right? For example, Fourier series is a commonly used one. So here, just to demonstrate the difference between multi-stage neural network compared with classical Fourier series, it tends to perform really well for functions that are smooth but non-periodic. So for example, here is another simple function. And again, for multi-stage neural network, we have this 1/6 scaling. If you do a fast Fourier transform of this, the same function, you will get a steep, also a power law because that's due to the spectrum of the target function, but the slope is smaller. And so you can see the consequence of that. So now you can take second derivatives of the approximated function, and you can see that the second derivatives of the Fourier series approximation have very large error, while the second derivatives of the multi-stage neural network has a much smaller error. Of course, we know that Fourier series is very good for periodic functions. So here we also try an example of a periodic function. In this case, it's expected that the error of a Fourier series will converge exponentially. And you can look at the second derivatives, and Fourier series does very well. Multi-stage is also, because it's only second order, it's also doing pretty well. And so many people ask about this, so I include this plot. You can ask how efficient is it to get the error down with certain number of parameters. Again, the blue is the non-periodic function. You can see that for this non-periodic smooth function, if you use the dashed line is Fourier series, these dotted data points are from multi-stage neural network. So for the same number of parameters, if you want to go to very high precision, using multi-stage neural network to express the function can give you 5 orders of magnitude reduction of approximation error. Of course, if you have a periodic function, then you should just use a Fourier series. And in terms of computational time, again, this is just function fitting, okay, nothing fancy. Computational time, we observe a crossover regime. If you want to do a very, very accurate fitting, so you want the error to be really close to machine precision, it turns out it's faster to do a multi-stage neural network compared to the Fourier series, which is this dashed line. Okay, so that was just 1D function. Here I will show a very simple example of extending this to higher dimension data. Here my student Jenkins, she run a classical numerical solver using the spectral methods to create multi-scale data from this 2D incompressible Navier-Stokes equation in a vorticity form. So here is the numerical solution or vorticity evolving with space and time. And I like this example because it's a very simple example of multi-scale function where the energy spans over 2 orders of magnitude in wave number. So if you just ask the question, how accurately can a neural network fit such a flow field? This is our target function. This is a string function from the numerical solver. And this is a neural network. And of course, you can fit one single neural network with reasonable precision. So this is the error between the target and the first neural network. However, if you look at the energy spectrum, here the block line is the target energy spectrum from the numerical solution. The blue line is from the neural network, and then you see that the neural network can only capture small wave number because it's capturing the large scale feature, but it's really missing the spectrum at higher wave number. So it's missing the small scale details, and this is what I mentioned in the very beginning of the talk because of the spectral bias. So we can analyze the error of the first neural network looking at it in Fourier domain, and then you can see that the error has a dominant frequency. So now we're going to train the second neural network to approximate this error. And importantly, because now the error has, we know the dominant frequency of the error, so you can use that information to optimize the neural network weights when you design the second stage neural network. So now this is the error of the second stage neural network. The error is 10 to the minus 7, and the error now has a higher dominant frequency in the Fourier domain. And if you see the energy spectrum, now you're capturing the energy spectrum with a wider range of wave number, but you're still missing the highest wave number. But you can just keep adding stages until eventually the error goes down to close to machine precision, and the energy spectrum is perfectly captured by the multi-stage neural network. So this is just a brief comparison. We show that multi-stage can tackle the spectral bias of neural network. The gray line here is the target energy spectrum. If you use a single neural network, you will most likely get something like this, like the red line that present the spectral bias problem. The multi-stage neural network can resolve this issue. And if you look at the loss convergence, essentially when you add different stages to the multi-stage neural network, you're increasing the expressiveness of the neural network by having subsequent neural networks. And that's a very effective strategy to boost the approximation accuracy. In this case, it's close to machine precision of the double precision floating point. And if you use the same number of parameters for just one single neural network, you most likely will see a limited accuracy. Okay, so just a summary plot. Actually, this algorithm can be automated. All you need is the error from the previous network and the frequency of the error of the previous network, and then you can use that to design the subsequent neural networks. Okay, so here's the fun part. We have shown that this multi-stage neural network is a very good functional approximator. So can we use it to find PDE solutions numerically? And I will just talk about a very brief example, but a lot of the details is in a paper with Yangji that was published earlier this year in Journal of Computational Physics. So earlier I mentioned neural network is functional approximator. If you want to use it to approximate solutions to PDEs, you can simply add the equation into the loss function. So for example, if you are trying to solve this PDE or ODE, you can evaluate, you can substitute the neural network prediction into the equation and then quantify the so-called equation residue. So equation residue is a very important concept that will keep coming up throughout the rest of the talk. Equation residue will be 0 if your solution is perfectly correct. So here, simply because neural network is an analytical function, so you can calculate all these derivatives analytically, and then calculate this equation residue. And all we need to do is to include this residue into the loss function as the equation loss term. So now the neural network is trying to find a set of weight and biases such that its prediction closely satisfy the prescribed equation. So a simple ODE as an example, again, you have the equation residue. And now we say that our solution can be written as a superposition of the first neural network and a subsequent neural network. Here's an example of a simple ODE. Here we also have the exact solution. So with one single neural network, you can see that the solution is represented by this red dashed line. And you can look at the equation residue for the first neural network, in this case, 10 to the minus 7. And you can now, this residue is just using one single neural network. But now after you add the second neural network, you can evaluate the residue of the two neural network, where the U0 is known because it's from the previous neural network. U1 is this additional second neural network that you're trying to solve for. Epsilon 1 can be estimated based on the error of the first neural network. So now after the second stage neural network, the error can go down to 10 to the minus 11. And here is just showing the convergence of total loss function, the equation loss function with iterations after first, second, and third stages. So it can be very accurate. And yeah.
Mike. The question I was asking before, if you go just one slide before this one.
This one.
And we can discuss it later, is in these losses, is how do you get the xi's and the xj, and what is the scaling that you need for nd and nf in order to achieve the machine precision that you get later on? That's
how do we decide this nd and nf, right?
And also whether you do that by fixing the set of x's that you have a priori, or if you redraw them at every stage, if you put them on a grid, or what is it? That's the okay.
We have to redraw.
I understand it's a technical step, but
we have to redraw. But that's a good question. We have to. You can actually use as many nd as you want or nf, but we have to redraw it for the second stage, because second stage we're trying to fit higher frequency functions. So you need more. Naturally, you need more sampling points. that
about the scaling, because it's going to have an impact on the
scaling,
cost.
the
We can discuss that later.
Okay.
So it's just
the
to
scaling
precise
should
the
be
question.
right. Scaling should be related to that 1/6 I talked about earlier. But yeah, let's talk more. I want to make sure I cover the really cool part towards the end. So yeah, I'm going to show that we will use, we can actually use this neural network to find singularities in fluids, and this is the work led by Youngji in collaboration with Tristan, who's a faculty member here, Gonzalo, and Javi. So just to show you what we're trying to do, this is a very simple example of the implicit Burgers equation. And this is the Burgers equation exhibit shock formation. So here, as you can see, the solution evolved with time and then form a very steep gradient in the middle at a finite time. So if you look at this problem in the so-called self-similar domain, that's defined by this red box. So if you follow the solution in this red box, and now look at this solution in the self-similar coordinate, we can see that the solution gradually approach a stationary or steady-state self-similar solution, which is shown by this orange curve. So we're trying to find this orange curve, basically, for the equation. So first thing you can express the solution in the self-similar coordinate, where lambda is the self-similar exponent that we don't already know. That's something we're trying to find as well. And we also want to find the solution in the self-similar coordinate. So we're trying to find capital U as a function of the self-similar coordinate. And this is expressed as y. And at the same time, we're trying to find lambda. So the original PDE can be now written in the self-similar coordinate as an ODE. And again, the goal for the neural network is to find the solution, so capital U as a function of y, and find the self-similar exponent. So this is actually an inverse problem, because if you know lambda, if you know specify lambda and want to just solve for u, it's actually a trivial problem. It's a forward problem. But here we are trying to find both the solution profile as well as the unknown parameter lambda in the equation. Okay, so here is how it look like when we are training a neural network to approximate to solve this implicit Burgers equation in a self-similar domain. You can see that in the first stage, the error is about 10 to the minus 7. Second stage, the error can become really, really low, about 10 to the minus 14. These are the equation residue. For this problem, we know the analytical solution, so you can actually compare the final solution with the analytical solution. In this case, it's actually really close to machine precision, close to 10 to the minus 15. And you can just see how the error converge with iterations. Okay, so that was a very simple example. And now we want to look at if we can use this strategy. Yes? Yeah, we can find the second higher order smooth solutions. Yeah, so good question. And yeah, so here we want to use this for the incompressible orders equation. Essentially, the question of interest is whether there exists smooth finite energy initial conditions that can lead to a solution to the incompressible 3D Euler's equation that will blow up at a finite time. And in the past decade, there has been compelling numerical evidence using direct numerical simulation that is suggestive of singularity formation to incompressible 3D Eulers. And here, we want to see if we can leverage neural networks' expressiveness, because it's a very good functional approximator, to find highly accurate blow-out solution numerically. And here we consider the Luo-Hao blow-out scenario. So here is a simulation that was done by Luo and Hao in 2014, where they solved the equation directly in space and time domain. So this is a direct numerical simulation, and then they show that if you impose a cylindrical boundary, here is a flow field in a vertical plane. You have flow going downwards, going upwards, and this is the point where they observe dramatic growth of vorticity, and that is suggestive of singularity. So here we consider this scenario and then write everything in a self-similar coordinate. Again, this lambda is an unknown parameter, the self-similar exponent we are trying to find. And the set of equation can be reduced to this following 5 equations. It's also the Boussinesq equation. And so here is the neural network setup. Now we're trying to find a set of a set of numerical solution profiles. That's the output of the neural network as a function of 2 input, which are the 2 self-similar coordinate. I want to mention you should do this in the self-similar coordinate, not in the original time and space, because that becomes a really hard problem. And here we input the 5 set of self-similar equations into the cost function. And throughout the iterations, the neural network try to find a set of solution profile that closely satisfy this set of equations, and also try to find the unknown parameter lambda, which is a self-similar exponent. There are actually many things I really like about this approach, because you can impose structures to help the neural network to find a solution. For example, you can impose symmetry constraints. For example, we know some profiles are odd, some profiles are even. You can construct the symmetry by defining the solution profile as a neural network like this. If you want odd symmetry, such that your final U will be an odd function by design. We can also add smoothness constraint, and this is related to your question earlier about how do we find a higher order smooth solution. So for example, maybe we want solutions that are, we want to avoid solutions that are non-smooth. What you can do is to penalize the gradient of the equation residue near the points where we know the solution might be non-smooth. So you're trying to penalize the behavior like this, for example. You can put that in the cost function. And finally, we can use change of coordinate to map infinite domain in the original coordinate system to a finite domain in a new coordinate. For example, if we use a hyperbolic sine function, you can effectively map infinitely large domain in the original coordinate into this finite new coordinate z, and your neural network can solve the set of differential equation in this z coordinate. And this gives you the benefit that you can now describe not only the solution structure near the origin, but that solution also expand to a really far domain. So this is just to show how it works. Throughout the training iterations, the loss function converges over iterations, and a neural network find a set of numerical solution profiles that exhibit finite time self-similar singularity to the 3D incompressible isosymmetric Euler's equation with the presence of a symmetrical boundary. And because these neural networks are analytical functions, so you can easily quantify the equation residue by substituting this back into the equations and then look at the residue of the solution. And since then, so this was published last year in Physical Review Letters. This was just using single neural network, but we also have tried to use the multi-stage neural network. So you can see after the second stage, you can further push the error down. Here, we actually have a equation residue that's down to 10 to the minus 13 after the second stage. And in this case, the solution is really close to machine precision of the double precision floating point. And in this case, the inferred self-state exponent is more accurate. And I should mention that the singularity has been proved by Chen and Hao in this preprint. And in their paper, they also have they use a more classical method and obtain a self-state exponent that's very close to ours, up to 7 digit after the decimal points. Okay, so this is something that's really exciting because we can also use this type of strategy to find solutions that are unstable. So here is an example of the CCF equation, and throughout iterations, the equation residue converges, and the neural network finds a set of numerical profile. So here it shows that a neural network can find both smooth stable solution and smooth unstable solution. So the stable one is the blue curve. So here we're solving for both vorticity and velocity. And the unstable smooth solution is the red dashed line. And the difference between those two in the numerical implementation is that we add different smoothness constraints. So we have a higher order of derivatives of the equation residue imposed in the cost function for finding the unstable smooth solution, because this unstable smooth solution is surrounded by non-smooth solution with higher order of differentiability compared to the non-smooth solution around the stable smooth solution. Does that make sense? Yeah. Yeah. So here you can look at the. This is also using the multi-stage neural network, and the PDE residue is down to 10 to the minus 9. I should mention that in general, unstable solutions are really hard to find using the classical time-stepping simulation because of the instabilities in the equation. Okay, so what's next? Here we show that multi-stage neural network can enhance the expressiveness of neural network and give you highly accurate numerical solutions. We're right now interested in exploring varying unstable solutions using this technique. We're also interested in using multi-stage neural network to find high precision PDE solutions, doing a systematic study on what kind of PDE is it good at compared to more classical methods. And also I'm very interested in, from the ML side, understanding what gives rise to this scaling law of the multi-stage neural network. So also, why do we want machine precision? It's useful because you can test hypotheses about the solution structure. For example, you can, if your neural network expressiveness is no longer the limiting factor, you can effectively test what the correct constraints you need to impose. You can test, for example, smoothness. How many orders of derivatives do you need to take to find a smooth solution? You can impose what are the correct symmetry to impose that can lead to smaller PDE residue. Okay, so what have we learned? We showed that this neural network is a very, you can tackle the spectral bias and it can approximate machine precision. This is useful for multi-scale, for representing multi-scale function accurately. And you can use this to find highly accurate PDE solutions numerically, for which Fourier series may not provide optimal basis function. For example, for some of the solutions that is not periodic, you can imagine that spectral method may not be as desirable compared to expressing the solution with a multi-stage neural network. And it can be used to search singularities in fluids more broadly for finding solutions by imposing mathematical structures. We showed that you can find unstable block solutions that can be otherwise difficult to find. And importantly, this requires a lot of mathematical knowledge to guide the neural network to find the right thing. With that, I want to thank my wonderful collaborators, especially Yangji is really doing a tremendous job leading the project. If you're interested in multi-stage neural network, the code is open source, freely available, and encourage you to check out this GitHub link, and our list of publications is listed here.